The first problem we're going to look at is actually number 7 on the slide. The question is, what is the ratio of the length of the arc DE to the length of the arc BC? So what we're looking at is we are going to set up a ratio of this arc right here to this arc right here. And as you notice in this problem, they don't give us any numbers, right? We just have a lot of variables. So they're calling the radius for this arc here r/2. They're calling the radius for this one just r. These, those are betas. Those are just another way that we are going to use a Greek letter as a variable. So this could also say 2x, and that could say x, but it doesn't, so we're going to use the beta, so 2 beta and beta. So I'm going to go ahead and move over to the board then, set the problem up, and do it. All right, so here we have our setup. So we're looking at the ratio of the arc of DE to BC. So we need to use our arc length formula. That's what that is. This is the arc length formula for DE. Remember, this is our central angle, which they call beta, and then we're going to multiply it by 2 pi, and then the radius for that little piece there was r/2, and then that all goes over 360. And then for BC, we're going to look at the central angle. That's called 2 beta. And then we're going to multiply that times 2 pi, and then the radius for that section there was just r, and then we divide it by 360. Okay, so we're setting up the ratio of these arc lengths by using the formulas and just plugging in the variables that they gave us. All they gave us were variables. So what this really becomes is a really nice algebra problem. So if you remember, just when we're working with fractions, if we have one fraction, like if we had 1/4, and it was divided by another fraction, like 1/2, the way we would solve this is we would take what's on the numerator and we would multiply it by the reciprocal of the denominator. Okay? And then we just keep going. Well, we're going to do the same thing with this. So I'm going to erase, so I've got some room here. We're going to take our numerator, so we've got b times 2 pi times r/2 divided by 360, and then we're going to multiply it by the reciprocal of the denominator. So this is our fraction, so we're going to flip it. So the 360 would be in the numerator, and then the denominator is going to be 2 beta times 2 pi r. All right, at this point what we want to do is just start canceling. So I see that I have 1 beta here and a beta there, so I'm going to cancel those. I also have 2 pi here, and I've got a 2 pi there, so that's gone. I have a 360 here and a 360 here, so that's gone. And then I'm going to take what I've got here, and I'm just going to go ahead and write it over here. So I have r/2 left in the numerator, and then I have a 2r in the denominator. All right, so now I have a fraction and I'm dividing it by something, so I want to use my same method. I'm going to take whatever is in the numerator and I'm going to multiply it by the reciprocal of what's in the denominator. So that would be 1/2r. All right, when I do that then, I want to see what I can cancel, so I can cancel my r's. So what that leaves me with is a 1 in the denominator and a 2 times 2, 1 in the numerator and a 2 times 2 in the denominator. So that means my final answer here is 1/4. So what we're saying is that the ratio of this arc to that one is 1/4. That's our answer. For this problem, I know it says number 1. This is number 9 in your slide. So for this one, it tells us we have points A and B lying on a circle, the center is 0, and then it tells us this length of AB, the arc AB, over the radius is equal to pi/10. And the question is, what's the ratio of the area of a sector AOB to the area of the circle? So we need to kind of dissect this problem. So I'm going to go over to the whiteboard, and the first thing we're going to talk about is just this little piece right here and what that really means. Okay, so we're just focusing on that one little piece of the problem. So that problem says length of AB over R. So there's a key concept in the tutorial that said that theta is equal to the length of AB over R. Theta, again, is just another Greek variable that we're going to use, but what it really means is the angle measure. So the angle measure of that circle is equal to the length of AB over R. They told us that this is equal to pi over 10. So what they are essentially doing is they are giving us the angle measure, and that angle measure is in radians. So what we can get from this little piece of the problem is that the central angle is pi over 10, and it's in radians. So we're going to convert this to degrees. And the way we're going to convert from radians to degrees is we're going to multiply whatever the radian measure is times 180 over pi. That's the way we're always going to do it. We're going to take the radians and we're going to multiply by 180 over pi. You'll kind of recall it's really like the opposite of what we did when we started with degrees to get radians. So our answer then here is going to be these cancel, and 180 divided by 10 gives us 18 degrees. So what we know is that this is the central angle on that problem. The next part of the problem we're going to focus on here is the question: what is the ratio of the area of sector AOB to the area of the circle? So we're going to go back to the whiteboard now that we know that that central angle is 18 degrees, and we're going to use another ratio to figure this out. So we know the central angle for that problem is 18 degrees. There's another ratio or key concept that was in the tutorial, and it says that the sector area over the circle area is equal to the central angle over 360 degrees. So that was in the tutorial. So in essence, what we know is they're asking for the ratio of the sector area to the circle area, but that's the same thing as the central angle to 360. So since we just found the central angle, which is 18 degrees, we're just going to plug that in, and that would be the same ratio as the sector area over the circle area. So now we just want to reduce it, and it reduces to 1 over 20. So that ratio is 1 over 20. Sector area to circle area is 1 over 20. For the last problem, this is number 10 on your Google slide. It says points A and B lie on a circle centered at point O. If OA is 5, so that means that's the radius, and then we have the length of AB over the circumference is equal to 1/4. We're trying to find out what's the area of the sector AOB, and we are going to use 3.14 instead of pi. So we want to focus in again on this little piece of information. This is important what they tell us. Length of AB over the circumference is equal to 1/4. So we're going to go to the whiteboard and talk about that. And then remember that in the end, what we're trying to find is the area of the sector AOB. All right, so we're focusing in on this, length of AB over circumference. In the problem, it says that that's equal to 1/4. And focusing in on a key concept in your tutorial is that the length of AB over circumference is equal to the central angle over 360 degrees. So if we know that this is equal to that, then we can say that 1/4 is equal to this. So our setup here is going to be 1 over 4 is equal to our central angle over 360. And for the central angle, I'm just going to call that x. And so what we want to do is just solve for x. So that gives us, I'm going to cross multiply. 4x is equal to 360. So x is equal to 90 degrees. So what that means is in the problem, we know our central angle is 90 degrees, and we found that by using these key ratios. Okay, so the last part of our problem is asking for the area of the sector. We found out that the central angle is 90 degrees. So now we can just go back to that formula that we looked at on day 2. And now we know that 90 degrees is the central angle. So we're gonna take that 90 times pi times our radius, which our radius in this problem was 5. So we're going to take 5 squared and divide it by 360. So we put in our formula, and that ends up being 19.635, which I think the answer is to the nearest 10th. So that would be 19.6. All right, This is Tyler. He didn't know I was going to do this, but I wanted to say a big thank you to him because he's been recording all these videos. All right, that's all we have for this week.